So hello all. So today we are going to solve a very important question of gate operating system which came in 2015, and it involves the concept of virtual memory and address translation. So before we go into the question, let us briefly understand this concept of address translation from virtual to physical. So it's going to be like this. So this is our CPU, and this will generate the virtual address, and this is of this form. So we have this virtual page number. I'll be denoting it with VPN, and then we have this offset. Okay. Okay, fine. So, and after this we have this mapping. This is a page table. Okay, and for each corresponding virtual page number we have one address of the frame number which actually exists in the physical memory. So for each virtual page number we are having a corresponding frame number. Okay, so this is the frame number address here, and this will be after this mapping we will have this is the frame number, and this is the offset. I'll represent the offset with D, and let us just give a short notation for this as well, V. Okay, so this offset will be copied as it is to the physical memory address space. It will be like this. Okay, so for each virtual page number we got the frame number address, and from this we got this part of this physical address, and the offset, that is D, that this will be copied as it is into this. So we have this physical address here. This is the physical address, and we have this memory. Okay, and this is the actual frame where the desired data is there, and that can be used by the processor to get the processing done. So we have a virtual address space for each process. Okay, so this is how this translation is happening here. So now let us understand the question. So the question says we are having, let me change the color once. So the question says we have 8 kilobyte of pages. Okay, fine. So this will translate to 2 to the power 3 into 2 to the power 10, and that is going to be 2 to the power 13. So it means that we will require 13 bits to represent this 8 KB page size. Okay, so this is the page size, and now with we represent the page size with this offset. So we can say that this offset will require 13 bits for offset. Okay, so this we got, and then what it says, each page table entry contains a valid bit, a dirty bit, 3 permission bits, and the translation. Okay, so apart from this frame address we have few extra bits in the page table as well, the valid bit, the dirty bit, and few more. Here the translation bit is given. So valid bit, it tells like if the page is a valid entry or not, page address. Okay, and then this is this dirty bit. It tells if the frame has been, or the page has been modified or not. If it is set to 1, it means that it has been modified, and if it is set to 0, it means that it has not been modified. So pretty simple. So these are the extra bits here, and the maximum size of the page table of a process is 24 megabytes. So this page table as per this question is 24 bytes. Okay, sorry, megabytes. Okay, this is 24 megabytes, and the length of the virtual address supported by the system is okay. So it asks us to find the length of the virtual address supported by the system. That means we need to find this length. Okay, so we are clear like what the question is asking and what we need to do. So let us move forward. Okay, so let us draw the physical address space once. Okay, it will be useful for us. So we got the offset bits, that will be 13, and it's mentioned that this is a 32-bit physical address space. Okay, This is 32-bit of physical address space. So we will have the frame number as 32 minus, okay, 13. Okay, so we will have 19 bits for this frame number, or you can also think it like this, since this is a 32-bit address space, so the total size will be 2 to the power 32, and since each page is of 8 KB, so we can write it like this: 2 to the power 13, and 8 KB will translate to 2 to the power 13. We will have 2 to the power 19 frame number frames, 2 to the power 19 frames in this physical memory for this processor. So this will roughly require total how many bits? 19 bits. So you can also get this 19 bits information for this physical memory. Okay, so this is 19 bits, so it will represent 2 to the power 19 frames in the physical address. Okay, now what does this frame number contains? This is sorry, this is the address of the frame in the physical address. Okay, so to represent 2 to the power 19 frames, we will require 19 bits. Okay, and this is going to be the, okay, okay, let's just see one more thing. So the second part, it says like we have a valid bit, one is valid bit, and one is dirty bit, and three permission bits, and the rest of the things are translation bits. So what will be the value of this translation bit? We will get it from here only. So this will be the 19 which we are having here. This is the translation bits, okay? Because we need to just map to 2 to the power 19 frames in the physical address. So we will require 19 bits for this. It will be a 19 bit field. Okay, so this translation bit will be 19 here. So now let us see how many bits we are getting here. Total number of bits: 1 plus 1 plus 3 plus 19, and that is going to be 24. So this is 24 bits, and it will be 3 bytes. Okay, so it is an important step here. So never forget to just translate it to bytes, else we will get the wrong answer. Okay, so let us move forward. So yeah, each entry in this page table will be of how many bytes? It will be of 3 bytes. Okay, and it has been given that total page size is 24 megabytes. So we can get the total number of entries here, and let's see. Total number of entries will be 24 MB by 3 MB. We can do it, and that will be going to be 8 mega, and that will be 2 to the power 3 into 2 to the power 20. Mega is 2 to the power 20, and that will be 2 to the power 23. Okay, so these many entries are present in the page table, and as mentioned earlier, uh, each virtual page number will have a corresponding entry in the page table. So there are 2 to the power 23 virtual page numbers, and to represent them, how many bits we will require? It will be log, we can take log of 2 to the power 23, and that will be 23 bits. Okay, so it will be 23 bits. So let us draw this. Okay, so for virtual page number, how many bits we got? We got 23 bits, and offset we already saw it was 13 bits, so it will be 13. And what is the total length of this virtual address space? It will be 23 plus 13, and that will be 36. So 36 is the answer. Okay, so 36 is the correct answer. So I hope that you understood this question pretty well, and the concepts behind like how to solve it. I'll be posting more videos regarding it previous year questions of various subjects as of now, and in future I'll also post videos related to the concepts and topics as well. So do subscribe and like and let me know in the comments if any doubt. Thank you for watching.